So we're on question 7. An algebraic method to find the square roots of the complex number 5 plus 12i. Remember, this is a kind of standard start to a question. That means that if we set our number as being x plus iy squared is 5 plus 12i. That's what we're looking for, isn't it? Because that means that x plus iy is the square root of 5 plus 12i. So we multiply that out to get x squared plus 2xyi plus I squared y squared. But I squared is minus 1, so that's minus y squared is 5 plus 12i. That's what we always do. That's a standard start to this. We know that this is what it leads us to. We're now comparing real and imaginary parts of this expression. So we're saying if we look at the real parts, x squared minus y squared is 5. If we look at the imaginary parts, 2xy equals 12. So because that's just such a standard start point, this is where you started getting marks here, was for getting these equations at this point. We now need to solve these equations simultaneously, and it's a thing that we do quite often. What could we say? Y is 6 over x. Divide both sides by 2x. So we are going to, well, I hadn't realised that the joke was coming out, but we're going to have a sandwich at a well-known national chain of sandwich restaurants who have never given me any free stuff. We're going to sub y into the other equation to get x squared minus 6 over x squared equals 5. Having made that, look, I've never thought about that before, but I should be getting free stuff, shouldn't I? I'll keep you posted if a sandwich drops through my letterbox. That would be exciting. X squared minus 36 over x squared is 5. We have a stealth quadratic. We love stealth quadratics. Multiplying 2 by x squared, x to the 4 minus 36 is 5x squared. So x to the 4 minus 5x squared minus 36 is 0. Does it? Oh, don't know. Let's see. Does it factorise? Oh, it's exciting. 9 and 4. They look like good numbers. If we have x squared minus 9 and x squared plus 4, yes, there it is, factorised, giving us that x squared equals 9, or x squared equals minus 4. However, the whole point of this is that our complex number that we're looking for has real parts, x and y. Implicit in what we're doing here are the fact that x and y are real. If x and y are real, x squared can't be minus 4. Which leaves us with x squared being 9, so x is plus or minus 3. If x is plus or minus 3, y is 6 over x. So if x equals plus 3, y is 6 over 3, which is 2. If x is minus 3, y is 6 over minus 3, which is minus 2. So we've got the numbers. It was x plus yi, so it's 3 plus 2i and minus 3 minus 2i. There we go. They are our roots of that equation. For 5 marks, there's nothing in there at all, is there? That could have been the first time we ever did that. That could have been the example that we've got in our notes. Straight through a standard finding the roots of complex number. Hence solve the quadratic equation x squared minus 4x minus 1 minus 12i. Okay, this is maybe a little bit of a new twist to this. We don't do this all that often, but still it's not a big deal. Minus 4x minus 1 minus 12i is 0. Oh, that was an x, wasn't it? We've got a choice here. There are 2 ways that we attack this. We either go straight for the formula, if we're formula kind of people, or we go straight for completing the square, if we're completing the square kind of people. Completing the square is a bit more elegant. Doing the formula is probably a bit more likely the safe route that most people will do. What should we do now? Let's vote. Votes for the formula. We have 2 votes, 3 votes. Votes for completing the square. We have 4, 5. Completing the square has aced it. Right, we're completing the square on this one. If you're doing the formula, of course, remember that in the formula A is 1, B is -4, and C is all of this. -1, -12i. So that's what you're putting into your formula. But anyway, that's not what we're doing. We're completing the square. Mega. So completing the square gives us x squared minus 4x. To complete the square on that, we would need a +4, wouldn't we, to be alongside that, to make that a perfect square, because a half of -4 is -2, squared is +4. We've still got the -1, -12i hanging around there. We've just added a 4, just because we felt like it, so let's take that 4 away again. It's all equal to 0. This gives us x minus 2 all squared, at which point we're going to throw everything over to the other side, and we'll be met by not much of a surprise, because we're going to have 5 plus 12i. Oh, astonishing! Have we seen that before? No way! There we go. So 5 plus 12i appears at that point, telling us that x minus 2 is plus or minus the square root of 5 plus 12i. Oh, if only we knew what the square roots of 5 plus 12i were. We do! They are 3 plus 2i and -3 minus 2i. Who would have thought that? So there we've got x is 2 plus or minus 3 plus 2i, because they're the roots, aren't they? And we've just, I think you got the marks for writing that, actually. I would feel that I'd want to tidy that up. I'd want to say that x is 2 minus 3 is -1, minus 2i, and the other one is 2 plus 3 gives us 5 plus 2i is the other one. So if we take the positive, and there we go. There's our roots of the equation. If you did, of course, if you did the quadratic formula, the same thing happens, doesn't it? You end up with 5 plus 12i inside your square root. I actually think, do you end up with 20, is that right? 20 plus 48i, and you have to take 4 out as a factor, which then square roots to 2, and it cancels with the 2 on the bottom, and you get the same deal. You get 5 plus 12i inside the square root. There we go. And that's maths.